Now a function is said to be continuous at x equal to a if limit exists and the limit is equal to the function value. So left hand limit is equal to right hand limit and equal to function value at a, then function is said to be continuous at a. So graphically it means like at that particular point at x equal to a, at x equal to a, we should be able to draw the graph without a break. So let us take an example. So f of x, first example, example 1, f of x is x minus 1. So if I have to draw the graph of x minus 1, how will I draw it? When so y equal to x minus 1, this is what I'm plotting. So when x is equal to 0, so when x is equal to 0, y is equal to minus 1. So this is the point. And when x is equal to 1, y is equal to 0. So these 2 points we need to connect. So this will be a straight line like this. Now, let us say at x equal to 1, I am trying to, so when I drew the graph at x equal to 1, I didn't find any break. I just drew. I joined the line. I didn't have to lift my pen to do it. So it is continuous. The function is continuous. Now we are looking at x equal to 1. So we say function is continuous at x equal to 1. Now in contrast, let us take another example. F of x is equal to modulus of x minus 1 upon x minus 1 for all x not equal to 1, and it is 0 for x equal to 1. Now this is a piecewise defined function. How will the graph be? Now when x is less than 1, it implies x minus 1 will be negative, which implies modulus of x minus 1 will be equal to minus of x minus 1. Therefore, modulus of x minus 1 upon x minus 1 will be equal to minus 1. All right. Now, when x is greater than 1, which implies x minus 1 is greater than 0, then it means modulus of x minus 1 is equal to x minus 1. Therefore, we get modulus of x minus 1 upon x minus 1 is equal to x minus 1 by x minus 1, which is equal to 1. This is equal to 1. All right. So this function is now defined like this. This is equal to minus 1 when x is less than 1. It is equal to 0 when x is equal to 1. And it is equal to plus 1 when x is greater than 1. So how will the graph be? When we have to plot the graph, x, y. Now when we have to plot the graph, the reference point will be this x equal to 1. Because here, this is 1, say this is 2, 3, 4, 0, minus 0, 1, 2, 3, minus 1, minus 2, minus 3, so on. So when x is equal to 1, the function value is 0. When x is slightly greater than 1, the function value from all values greater than 1 is equal to 1. But when x is slightly less than 1 or for all values less than 1, the function values is minus 1. So now this particular graph, I have to draw the graph and I have to cross 1. I have to cross 1. However, I will not be able to draw this graph without having to lift the pen when I cross across 1. So this type of a graph is discontinuous at x equal to 1. Your left hand limit is not equal to right hand limit in this case, and it is not equal to function value. Whereas for the previous problem that we saw, the right hand limit of the function when x is tending to 1 from the right, the function value is tending to 0. Now when x is tending to 0 from the left, the function value is tending to 0, and the function value is equal to 0 when x equal to 1. So at 1, the function is continuous, whereas here it is different, limit does not exist. So that is the basic idea of continuity. Now, so continuity of a function at endpoints. Now let us say function is defined on a closed interval AB. Now at the left end, when we have, so this is 0, and let's say this is the point A, this is the point B. Now function is defined on this closed interval AB only. It is defined on closed interval AB. So outside of AB, it is not defined. So if I have to discuss continuity at x equal to A, that means at the left end. So f is said to be continuous at the left end if only the right hand limit of A, the right hand limit at A, that means limit extends to A plus f of x, will be equal to f of A. So for continuity here at this point, only thing we see is the right hand limit must be equal to the function value. Whereas here for the right end of the interval, if we are checking continuity, then we can only check continuity from the left because function is not defined at all at the right. So here at this point, continuity condition will be limit x tending to b minus f of x should be equal to f of b. Then it is continuous at b. All right. Now we have discussed continuity at a point. Now continuity on the entire interval. So continuity on the entire interval. So function is said to be continuous on an open interval, AB, if it is continuous at every point C belonging to the open interval. That means any point within the open interval, if function is continuous at every point in the interval, then function is said to be a continuous function on that interval. However, if a function is continuous on closed interval AB, then it should be continuous on the open interval AB. Then it should be right continuous at A, the left end of the interval. And it should be right continuous at B. Sorry, left continuous at B, at the right end of the interval. So the function should be continuous at all points within the closed interval, and it should be continuous at the endpoints taking one-sided limit. Then we say that function is continuous on that interval. Next, the kinds of discontinuity. Of course, this from a gate point of view, this classification is not so critical, but we'll nonetheless cover it because you get they will ask whether it is continuous or discontinuous, but understanding this is important. We'll, as a part of completing this, it will just take a few minutes. So kinds of discontinuity. They are discontinuity of the first kind and discontinuity of the second kind. The difference is in discontinuity of the first kind, the limits exist. However, limits are finite also. They're not infinite. They are the left hand limit and right hand limit. They are finite, and they exist. Now, removable discontinuity of the first kind. In the removable discontinuity, it is defined like this. Removable discontinuity. Limit exists. Left hand limit is equal to the right hand limit, but it is not equal to the function value. So removable discontinuity of the first kind. Left limit exists, but it is not equal to the function value. So I'm writing here. Left hand limit is equal to right hand limit. However, they are not equal to the function value at that point. Therefore, the function is discontinuous, but it is called removable discontinuity. Why removable? Why is it called removable? Because we can remove the discontinuity by redefining f of a. We will redefine the function value at that point to become equal to the limit value. Then it becomes removable discontinuity. Now, non-removable discontinuity means the limit does not exist. The left-hand limit is not equal to the right-hand limit. Left-hand limit is not equal to right-hand limit. Now, you can redefine the function, anything we can do, but we cannot remove the discontinuity. So this is called as non-removable or jump. So the example that we discussed here of this particular function, the second example, f of x is modulus of x minus 1 by x minus 1 for x not equal to 1 and is equal to 0 for x equal to 1. For a function like this is a non-removable discontinuity because left-hand limit is minus 1 at x equal to 1 and right-hand limit at x equal to 1 is plus 1. So I can, even if I redefine function value here at x equal to 1 to be minus 1, my discontinuity is not removed. If I redefine f of x at x equal to 1 to be plus 1, again my discontinuity is not removed. That's why it is non-removable discontinuity. So left-hand limit equal to right-hand limit but not equal to function value is removable discontinuity. Left-hand limit is not equal to right-hand limit is non-removable or jump discontinuity. In discontinuity of the second kind, at least one of the limit does not exist. Means one of the limit is going to infinity. It doesn't mean just that left-hand limit is equal to right-hand limit. It means in the second kind, either LHL is equal to infinity plus or minus, okay, or right-hand limit is plus or minus infinity. This means it is discontinuity of the second kind. So yeah. So let's take one example and close for today. Okay. F of x is minus 3x plus 4 for x less than or equal to 1, and it is 4x minus 5 for x greater than 1. Minus 3x plus 4 for x less than 1 and 4x minus 5 for x greater than 1. So find, examine continuity at x equal to 1. So simple. Now first step to do is at x equal to 1, what is the function value? F of 1. Now for x equal to 1, the function is defined by the first expression. Here equal to sign is associated with the first expression. So it is minus 3 into 1 plus 4, which is plus 1. Now left hand limit x tends to 1 minus f of x. So limit x tends to 1 minus, when x is less than 1, it is minus 3x plus 4. When x tends to 1 minus, it means x is less than 1. So function is defined by minus 3x plus 4. So we have minus 3 into 1 plus 4, which is equal to 1. Whereas the right hand limit is limit x tends to 1 plus f of x is greater than 1. So function is defined by the second expression, 4x minus 5. So we get 4 into 1 minus 5, which is minus 1. So we get left hand limit is not equal to right hand limit. So this is which kind of discontinuity? This is discontinuity of the second kind. Sorry, discontinuity of the first kind, because limits are finite. Left hand limit and right hand limit is finite, but it is non-removable or jump discontinuity. Okay.